The 60-year blind spot. We have spent 60 years mapping Earth's magnetic field using nothing but point source magnetometers, essentially flying blind through a forest, while only feeling the bark of individual trees. As of May 4, 2026, the SMILE mission is sitting on a launch pad in French Guiana, exactly 15 days away from taking the first wide-angle photograph of the magnetosphere in history. This is not about aesthetic imaging. It is about solving the data gap in global space weather models that currently rely on interpolation rather than observation. To see the invisible, SMILE uses a mechanism called solar wind charge exchange, and the physics of that interaction is the specific delta that matters. The charge exchange mechanism. The magnetosphere is invisible to standard optics because it does not emit or reflect visible light, but it does glow in soft X-rays through a process called charge exchange. When high-charge state ions from the solar wind collide with neutral hydrogen atoms in Earth's exosphere, they steal an electron. That electron drops into a lower energy state and releases a soft X-ray photon between 0.2 and 2.5 kiloelectron volts. By capturing these specific photons, the soft X-ray imager can finally define the exact geometry of the magnetopause and the bow shock. This transition from measuring local magnetic flux to global photon counting is what allows us to see the shield's movement in real time. Lobster-Eye micropore optics. Standard X-ray telescopes use heavy, nested grazing incidence mirrors that restrict the field of view to a narrow fraction of a degree, which is useless for imaging an entire planetary shield. SMILE solves this using micropore optics, often called lobster-eye mirrors. These are thousands of glass square pore channels just 20 micrometers wide, curved into a spherical surface that can focus X-rays across a massive 15.5 by 26.5 degree field of view. It is a mass-efficient engineering trade-off that sacrifices raw angular resolution for the ability to monitor the entire dayside magnetosheath simultaneously. However, even the best optics are useless without the right vantage point. The 121,000 kilometer constraint. To photograph the magnetosphere, you have to get far enough away to see the whole system, which means leaving low Earth orbit entirely. SMILE is targeting a highly elliptical, egg-shaped orbit with an apogee of 182 kilometers, nearly one-third of the way to the Moon. This specific trajectory allows the spacecraft to spend 40 hours of its 51-hour orbit at high altitudes, looking back at Earth's magnetic boundaries from a distance. The mission's recent 15-day launch delay was due to a technical check on a Vega C subsystem, a necessary precaution because once SMILE reaches that 121,000 kilometer peak, there is zero margin for corrective maneuvers or refueling. This orbital distance is the physical limit required for global imaging. The real implication. The success of the SMILE mission effectively ends the era of theoretical modeling based on sparse point data. By integrating the soft X-ray imager with the Chinese-built platform and European instrumentation, we are moving from guessing where the magnetopause is to seeing it move under the pressure of a solar storm. This mission bridges the data gap between the solar wind inputs measured by L1 monitors and the ionospheric outputs we see on the ground. For space weather strategists, the shift is from reactive alerts to predictive tracking. The real test begins on May 19th, when the Vega C must prove its reliability after the April production line delay. If the deployment at apogee holds, the first global X-ray map of our magnetic shield will redefine the precision of every space weather forecast for the next decade. Watch the 63-minute mark post-launch. That is when the solar panels unfold and the mission genuinely goes live. Subscribe for more